Hey guys, today we're going to be talking about the difference between mathematical and strong induction using an example. So with that, let's get started. I'll share my screen. Okay, and you should be able to see it now. So take a look at this mathematical induction proof, where we're showing that 2 to the power of n is greater than n squared if n is greater than 4. And I encourage you to solve it on your own or at least read through the proof and make sure you understand it because it's critical before jumping on to the difference. Okay, I am going to assume you've done that. So now we're going to dive into the difference between mathematical and strong induction. And so remember that induction usually has 5 main steps. First, we're defining P of n, which is our statement. And we see that, okay, P of n means 2 to the power of n is greater than n squared. And that's pretty much the same. If you look at our base cases for the strong induction, we're just showing for n equals 5 that P of n holds true. So P of 5 is true. And again, that's that's exactly the same. What changes though is the inductive hypothesis and the inductive step, which uses the inductive hypothesis. So usually in mathematical induction, we want to assume P of k, which is our inductive hypothesis, and use that to show P of k plus 1. So in this example, that would be like assuming 2 to the power of k is greater than k squared. But look at this mess that we have here. It looks a lot more complicated than this statement over than just saying P of k. And so how do we show this? How do we show that what this statement means in a more intuitive manner? And so what this is saying is that, okay, instead of just assuming P of k, we're going to be assuming all the values of k that come before it. So we'll be showing P of 5, P of 6, P of 7, all the way up until P of k when we want to prove P of k plus 1. So what does that mean in practice? Well, let's say we wanted to show that k is equal to, or P of k plus 1, which we'll just define as 11, is going to be true. What we're going to be doing is we're going to be assuming that P of 5 is true, and P of 6 is true, and P of 7 is true, P of 8, P of 9, and P of 10. And how do we get that information this kind of complicated way of describing that over here? What this is saying is that for all values of j that are essentially in between 5 and 5, which is our base case, and in between k, we want to assume that P of j is true. So again, we're going to be assuming that P of 5 is true. And then for all values in between that and k, remember in this case, k is going to be 10, so k plus 1 will be 11. And we want to show all those values in between are going to be true. And that's our assumption. And we're going to be using that assumption to show that P of k plus 1 is true, which is P of 11. Finally, you're going to be using that to conclude. So honestly, the difference between mathematical and strong induction for this example is not going to be very much. When we're going to be doing our inductive step, we're going to, instead of assuming that P of k is true, what we're going to do is assume for all j, 5 is less than or equal to j, which is less than or equal to k, that P of j is true. And then we're going to show, or want to show, that P of k plus 1 is true. So if we want to show that 2 to the power of k plus 1 is greater than k plus 1 squared, which would be P of k plus 1, then we would actually go about and do exactly the same steps that we did over here. Because strong induction, in reality, it's just giving us more information than mathematical induction is in order to assume. And the cost of that is simply going to be just using a slightly more complicated notation. But if we go through this problem, you'll see that we can assume the same steps. So 2 to the k plus 1 power is equal to 2 to the k, 2 times 2 to the k, just by algebra. We can say that this is going to be greater than 2 times k squared using our inductive hypothesis, because remember, we've assumed that P of k is true. Then we're going to show that this is equal to k squared plus k squared, again algebra, which is greater than k squared plus 4k. And we know that because k has to be greater than 4. Then finally, we're showing that this is going to be greater than k squared plus 2k plus 1. Again, we're showing that 2k is greater than 1 because 2k, k is going to always be greater than 4. And finally, we can say that this is equal to k plus 1 squared. Overall, that gives us exactly what we wanted. 2 to the power of k plus 1 is greater than k plus 1 squared. And what we saw is that in strong induction, in this case, it didn't really help us out much, but in many cases, it is going to make our lives a lot easier since we're going to be able to assume much more than in mathematical induction. Hope that helps. Bye.